Triv, will you do me the honours of filming a Brownian motion video with me?
Oh,
you okay?
sorry, yeah, I was apologised.
This might not be the video for you.
Oh, why not?
Well, there was this guy called Brown,
Right.
and he used pollen to demonstrate this Brownian motion thing.
Oh, that's handy.
But luckily for you, this is a toy, so I think your sneeze was just a
Oh,
one-off.
I think it was just a, yeah, that's fine, look. It's alright. But Brownian motion.
Brownian motion. So, first, let's go back to our model of what solids, liquids and gases look like, quickly.
Okay, so our solids are quite tightly packed.
Yeah, let's zoom in a little bit so the
Alright.
separation is actually sort of noticeable. We're zooming in quite a lot on a solid.
Okay.
It's still going to have this crystalline structure, of course, and these are really, really close together. But we say that they vibrate,
Yeah.
and we demonstrate that by just drawing these little wiggly lines around it. So it vibrates around this area, but it doesn't really move off anywhere, and they'll all do that.
It's a bit, the variations are quite random.
They're very random. It might just be all on that side.
Yeah.
You know, it's just really, really random movements. Then we go to a liquid.
Yeah. So we'll zoom in again, so it'll look quite similar to that, really.
Yeah, the sort of spacing will look quite similar. But we know that they're actually really close together as well. But they can flow over each other, so it's a lot more movement than here. Whereas here they're just shuddering about in their particular areas.
So here they'll be moving around a lot more.
Yeah, and there'll be a bit of overlap between the movement like that. It's Triv's drawn there. They
It's
overlap
a
a little
fried
bit.
eggs.
Bit like a lot of fried eggs. Yeah.
Yeah. They'll do that. Whereas gases, they're already very far apart. But if we look at them more zoomed in, like that, they'll move in quite straight lines, and they'll bounce off each other.
Bounce off things. And,
move. Haphazard motion, as they do.
And you're probably familiar with that. I just thought we'd mention that to start with.
And Brownian, this guy called Brown, kind of discovered this. So he was looking at pollen grains in water, as you do.
As you do.
And he noticed they were just sort of wobbling a bit.
Yeah, you put any pollen, something light, like pollen on the water, and it just moves if you look through a microscope.
It never stops moving. He was like, well, he thought, and quite rightly so, it was a bombardment of particles. He didn't think any further than that.
He didn't. Then this chap you probably heard of came along.
Yeah, Einstein turned up.
He did, he always does.
He
He basically took someone's idea and made it really good.
Yeah, he does that a lot actually, that was sort of his thing.
Yeah. And he said how small these particles must be, how quickly they must be moving.
And all this is very, very important, sort of understanding how particle physics works. So, using the conservation of momentum, we can look at that.
And the conservation of energy in particular.
Yeah.
So when things have kinetic energy, what does it really mean to have kinetic energy?
So you're moving around.
In a nutshell, it means you're moving.
Yeah.
So if we've got a particle with, what we'll say, lots of kinetic energy, and we've got a particle with, we'll say, less kinetic energy.
Alright.
And this one hits that one, it bombards it.
Yeah.
It's because of the conservation of energy, it's going to drop the pen.
Yeah. Can it equal out a bit more?
Yeah, and an example of this is because kinetic energy is proportional to temperature. So if we have some really hot water, say a cup of tea before you add milk, really boiling water, it's going to have, all the particles are going to have lots of kinetic energy. They're going to be moving around really quickly.
And as you add the milk, which is cold, normally.
Yeah, normally cold.
Then the milk itself will start moving faster.
Yeah, because it's going to be bombarded with these quicker moving particles, and eventually it will have some sort of thermal equilibrium. It will establish.
So as the water hits things, it will slow down because of this.
Yeah. And of course, in these scenarios, we're ignoring the heat given out, because it's actually going to be heat given out to the surroundings. As it hits the cup, it's going to vibrate the particles of the cup, the solid. It's going to vibrate more, and that's going to give off heat, which is why when you touch it with your hand, it burns.
Yeah.
But if we ignore that, it's just going to balance out, and that idea is important. This kinetic energy model, or the beginnings of it.
Yeah, being the kinetic model, and using that and conservation of momentum, he worked out how small the particles had to be.
Yeah. So we know mv is momentum.
Yeah.
We can work out change in momentum. We know how big the particle that the pollen grain that we're looking at is. We can work out how much that weighs. Based
on movement, we can work out how fast the thing was travelling and how heavy it was.
Yeah, so we can do both of those things. Einstein was a clever guy.
He was a very clever guy.
And
it's quite handy for looking at things. Before we mentioned that you can't see gas.
You can't, but when you have smoke particles going in,
then you can see it, and looking through a microscope, you can then model how they move.
So this is your microscope, say.
Alright.
This is your thing with smoke particles in it.
Yeah.
We've got a light source.
Yeah. I'll draw it. There you go.
Oh,
I've
orange.
helped now. I know. It's quite exciting.
You'll have some sort of refractive thing, so
Yeah,
a
so a
glass or
lens,
some
sort of a focus on what you're looking at.
And from GCSE, you know that these are light rays, they go into there. They're going to focus on a point.
And then when you look at the point, you can see stuff.
Yeah. You can see these particles moving about, and it's the same thing there. The gas particles are hitting the visible smoke particles, and you can see that happening.
Yeah.
And that's
Brownian
Brownian motion.
Yeah. It's based on a lot of past papers actually, sort of just asking questions about what it is.
Yeah. The question that commonly comes up is, what can you conclude from the Brownian motion experiments? You can conclude the velocity, and the mass, and all that sort of stuff.
Yeah, there is lots of smaller particles that you can't see doing things. Yeah.
What I've drawn up here, just in case you saw it, I'll draw it up roughly again. You don't need to know it very much. It's just the idea that in a set thing, when we say it reaches sort of an average velocity, some things, just by pure chance, will be going quicker. And so, in a given situation, you've got sort of this distribution a bit like this.
Yeah, sort of a bit like a Boltzmann distribution then.
So when that's velocity, and that's a percentage. Most percent, a great percent, will have sort of an average velocity.
Yeah.
So that's what's going to happen when they collide. They're going to get this equilibrium.
But some of them are going a lot faster.
Just by pure chance.
And some of them are going that sort of slow.
Yeah. And you just, that's something you might need to think about. Is that even when things reach room temperature, every particle in a cup of water at room temperature isn't going at exactly the same velocity.
Yeah.
And that's Brownian motion.
That is Brownian motion. With that in mind, I think we should demonstrate that with a cup of tea.
Absolutely.
Yeah.
So add the milk and it will cool down, right?
Yeah.